black hole per black hole as a quantum system. Take away that.
Okay, thank you very much, Atul, for asking me to fill in. I'm very happy to be giving a talk here. I've been coming to seminars for a long time. Yeah, so as Atul mentioned, I'm going to discuss some quantum mechanical aspects of the Kerr black hole. So the plan for where I'm headed is to sort of give a very broad discussion of black hole thermodynamics, how we think about it, and with our modern understanding of quantum gravity. And then I'll discuss sort of the history of the quantum systems that we've found for cold black holes. And then I'll wrap up with the new results that we have from a couple of months ago with some progress on the quantum mechanics of Kerr, which is sort of a difficult problem, which we can only sort of make incremental progress on. So this is based on work that came out in October with Ahmed Sheta, Andy Strominger, and Chiara Toldo. I think Chiara's in the audience, Ahmed too. Okay, and I've tried to aim this at sort of our broad general audience, so please, if there's any questions, feel free to interrupt. Okay, so I want to start with just one slide broad motivation for this topic. So about 50 years ago, physicists working on classical general relativity stumbled into a very suggestive and powerful analogy between, on one hand, the behavior of black holes in general relativity, and on the other hand, the laws of thermodynamics, as you learn about them in high school. And that analogy turned out to be extremely powerful. It's driven a lot of the progress in the field over the last 5 decades, and it informs a lot of what we understand about quantum gravity now. It's responsible for a lot of the progress. And the reason that people find this idea so interesting is that, you know, the laws of thermodynamics, we don't think of them as fundamental laws of nature. They are really emergent laws that come from a statistical or microscopic system controlled by other fundamental laws whose dynamics are very complex, ergodic, chaotic, okay? And we have a lot of evidence that black hole entropy, defined geometrically in general relativity, actually also has microscopic origin. So as I'll discuss, we think that there really are quantum mechanical systems whose dynamics gives rise semi-classically to black hole thermodynamics. In other words, black hole thermodynamics is supposed to be some coarse-grained approximation to these very complicated quantum mechanical systems. But on the other hand, black holes are just curvature in space-time. So if you manage to understand how it is that a black hole is actually a quantum mechanical system, then you've managed to say something about how it is that space-time can emerge from quantum mechanics. And that's really kind of the gold standard in quantum gravity, because most people believe that the nice, smooth, geometric description of nature that we experience is really some coarse-grained approximation to something which is more discrete. In other words, the fundamental description that includes quantum gravity probably won't make reference to smooth space-time. It's sort of an emergent collective phenomena that we encounter at larger distances and lower energies. Okay. So that's sort of why people have stayed interested in this question for more than 50 years. So maybe we bring it down to earth a little bit. So the subject really began with the discovery of the laws of black hole mechanics by a number of authors in the 1970s. You're probably familiar with the statement that there's a very short list of black holes in 4-dimensional general relativity. So if you ask for spherical symmetry, it's just the Schwarzschild black hole and the Reissner-Nordstrom black hole, if there's electromagnetism, those black holes are just labeled by their masses and their charges. If we allow the black hole to spin, then we have the Kerr black hole and Kerr-Newman, which is labeled by the mass, charge, and angular momentum. And all of these space-times are static or stationary, which basically means that from the outside, they don't evolve. They're kind of like equilibrium states. Okay. And those black holes, they come in families labeled by these sort of thermodynamic parameters, mass, charge, and angular momentum. And the black holes that are close together in these families, they obey relations. So if you take a black hole and you do some process that adiabatically or infinitesimally changes its mass, angular momentum, and charge, then the Einstein equation tells you that the area of the black hole's event horizon will change according to this balance law. Okay, so mass is just the ADM mass of the hole, angular momentum, charge, chemical potential, and the angular velocity are geometric quantities defined at the horizon. And so this is just a statement in classical general relativity. There's no H bar involved in its derivation. And formulas like this are actually more general than just Einstein gravity. So it's really a property of the diffeomorphism invariance inherent in the gravitational system. And there are generalizations of this formulas that involve higher derivative terms in the action. The only major thing that changes is this quantity that you integrate on the event horizon of the black hole. Okay, so this is a very general type of formula.
What do you mean by that? What does diffeomorphism invariance ever do to that?
Well, you see what this is not thermodynamics yet, right? This is just a statement about the Einstein equation and the family of solutions, but this formula relates things which are defined as spatial infinity, like mass, angular momentum, and charge, to something which is defined at the other boundary of the space-time near the black hole. So you're sort of dialing things here, and that's changing something at the event horizon of the black hole. The reason that that happens is basically because charges in general relativity are boundary terms, and that's a consequence of diffeomorphism. Okay. Yeah, so people derived this equation a long time ago, and there are more modern formulations like the Wolff formula. And it's also possible to show that there's a quantity defined on the horizon, the surface gravity kappa, which is constant when the black hole is static or stationary. So that sounds a little bit like thermodynamic temperature. And you can also show, using relatively elementary arguments, that if you have a black hole and it undergoes some evolution, the area of the event horizon always increases. So that sounds like a thermodynamic entry. Okay, so it was noticed pretty early on that these mathematical rigorous results in general relativity bear a striking resemblance to the laws of thermodynamics. But it's a little bit confusing analogy. For instance, what would the temperature mean in this scenario? Temperature is usually some phenomenological quantity that tells you when two different systems are in equilibrium. But if we put the black hole in contact with the heat bath, then the heat bath just falls into the black hole and disappears. Similarly, if you have a system at some finite temperature and you put it in contact with the vacuum, then the temperature is supposed to control the spectrum of emitted radiation, like a black body. But in our case, the black hole is just black. By definition, nothing comes out, so its temperature is absolute zero. Okay. So it wasn't immediately clear how powerful this analogy was going to be. And moreover, the quantity that actually appears in the first law of black hole mechanics, TDS, doesn't actually fix the absolute scale of the temperature or the entropy. We could rescale both of them. The form of the first law would stay the same. So we don't really even know what entropy to assign to the black hole class. Any questions? Okay. Now, the status of that analogy famously changed after a paper by Stephen Hawking in the mid-70s. The problem that he considered was quantum fields propagating on a fixed black hole background. So we fixed the background geometry. This is just a problem in quantum field theory. And what he showed is that for suitably smooth quantum states in this background, the far observer, located very far away from the black hole, actually receives faint radiation from the black hole, okay? And that calculation basically allowed him to fix the coefficient of the temperature and the entropy in black hole thermodynamics. So the entropy is the area by 4 in appropriate geometric units. Importantly, the temperature is proportional to h bar. So when you take the classical limit of these formulas, the temperature goes to 0, the entropy becomes infinite, and the black hole really is black, right? So that's sort of what you expect. We don't have h bar in general relativity. So in classical general relativity, the black hole has infinite entropy, but it's thought to be very suggestive that when gh bar is finite, the black hole entropy is finite, and that it scales like the area, not like the volume, okay? Normally, if you have a gas of a very complicated system, the entropy will scale like the volume of the system. Here, there seems to be a rather dramatic reduction in the effective number of degrees of freedom if the entropy of this black hole is scaling like the area rather than the volume that it encloses. Okay. So there are many different ways of deriving that result. It's basically a result in quantum field theory. Quantum field theory is on relatively strong mathematical footing, at least compared to quantum gravity. But the analog of that effect, when gravity is dynamical, leads to a very tricky puzzle, which we still don't completely understand. And that's because as this black hole radiates, if gravity is dynamical, then the black hole will begin to shrink as it radiates. And because the radiation that it is producing is approximately thermal, there's a lot of entanglement being produced. And the black hole will eventually disappear, but so far nobody has any actual quantitative description of how the information gets out of the black hole to purify the state of the radiation. We think it has to happen, but for a long period of time, the radiation appears just to be in some thermal mixed state. We think somehow the information has to get transferred out of the black hole to the far region, but nobody has really quantitative control over that calculation. So that may sound like you just can't make progress on this problem. It's not really the case, because it's possible to kind of split this question into 2 pieces. So there are kind of 2 different approaches, one of which is much easier to make progress on than the other. So the first approach just tries to just figure out what is the actual quantum mechanical system dual to this black hole. Okay, so this usually works in places where we can either ignore the evaporation process, so like a supersymmetric black hole that doesn't evaporate, or you put the black hole in an anti-de Sitter space so that it actually becomes in thermal equilibrium with this radiation, and it's not actually evaporating, and that buys you a long time scale where you can study the problem. And there's been, I would say, lots of progress in this particular approach to the problem. So this really began with a paper by Strominger and Baffa in the 90s. It was the first example where we identified an explicit quantum mechanical system that described the black hole, and that eventually got turned into the ADS-CFT correspondence, which is a huge piece of machinery which does allow you to discuss pretty explicitly microstates for black holes, but black holes in anti-de Sitter space rather than flat space or asymptotically de Sitter spacetimes. Okay, so in this approach, most of the calculations are relatively uncontroversial. You can even in some cases do mathematically precise calculations, but you kind of skirting the problem a little bit because you don't need to know all of the dynamics of the black hole in order to solve this part of the problem. Okay. The second piece of the problem is to understand how the black hole actually stores and releases information. How does it purify the radiation that it's sending out to Scribe Plus? And that's a much harder problem because it actually requires you to understand the dynamics of the black hole system. So in this approach to the problem, calculations are usually more controversial because ultimately you have to make some assumptions. We don't have complete control of the calculation, and eventually you really end up arguing about assumptions. And
but maybe it's logically possible you could do solve it without making assumptions.
Well, that's a little bit sort of what has been proposed lately, right? I mean, there has been a tremendous amount. So this is a very old subject with progress that occurred in the 90s. There's been, for the last 10 years, a lot of work on this part of the problem, which sort of culminated in papers which basically claim that well, maybe one or two major assumptions, but then you can sort of use the gravitational path integral to solve this part of the problem as well. I think, people still argue about that, but
I'm just saying it's logically possible to, isn't it, to give an argument that people won't argue?
Well, I don't know. That might be a sociological question, whether or not people will argue about it. But
the first thing, nobody argues about it. So
yeah, that's right. And yeah, I think most people after this updated their priors that they know how this is going to turn out. But unless you actually have a concrete model with controlled approximations, then it's still a little bit speculation, I would say.
Yeah, that was speculative.
Yeah.
Yeah,
no, I think this is a solvable problem, but we need to be more powerful and it will take more time.
Is all that work still in ADS or?
Most of this progress kind of uses things that we know in ADS and tries to turn it into a flat space problem. So for people who don't know, the major difference between black holes in anti-de Sitter space and black holes in flat space is that because anti-de Sitter space acts like a reflecting box, it's possible for a large black hole to come into thermal equilibrium with this radiation so that it doesn't actually evaporate. It's just like an actual equilibrium state. So the information puzzle gets translated instead into sort of exponentially long time questions about equilibrium states, questions about discrete spectra, that sort of thing. Whereas in flat space, this thing evaporates in a time scale which is polynomial in its size, so that the problem is sort of right in your face. And the major work that's been done here regarding the Page curve sort of tries to take a description in anti-de Sitter space, couple it to a flat space region, and use technology which we discovered in anti-de Sitter space to say something about the process. Okay, so splitting up the problem in this way is kind of like trying to study the spectrum of an atom separately before you couple it to the quantized electromagnetic field. Okay, so you could always try to study and understand the spectrum of bound states for an atom as a separate mathematical problem before you couple it to photons. So you imagine that there's some well-defined Hamiltonian that describes just the atom as some complicated interacting system. There's some Hamiltonian for photons, and then they couple in some way. So you try to solve this problem separately and then understand what happens when they get coupled, right? And normally what happens if you have a bunch of bound states sitting inside a continuous spectrum related to the electromagnetic field is that all of the bound states, they pick up finite widths, they have finite lifetimes, they eventually decay, but you still have pretty good control over the physics because you were able to solve this problem exactly, or at least approximately. So what we'd like to do is to have sort of a similar split for this black hole problem. So you can imagine that there's sort of some very complicated chaotic Hamiltonian that describes this isolated black hole system. There's some far region, which we understand pretty well because it's just waves and gravitons, and they're coupled in some way. So we try to solve this exactly and then include this sort of as a perturbative interaction, okay? So this is ChatGPT's understanding of an isometric embedding of the Schwarzschild black hole. It's not scientifically correct, but it's close enough for government work. And but actually, it gets the idea kind of correct for what I want to say. So the kind of cartoon that we would have is that there's sort of some description of a quantum system that controls the black hole or the region very close to the black hole. There's a Hamiltonian for the far region, which is just knows about small excitations, gravitational waves, gravitons, photons, things that we understand pretty well. And then they're interacting in this sort of overlap region, which we could think about incorporating using some Hamiltonian that describes coupling. One of the main difficulties is that there really isn't a diffeomorphism invariant way to make this split in theories of quantum gravity. Okay, so diffeomorphism invariance basically tells you that the Hamiltonian is actually always a boundary term. So you could kind of try to make this artificial split, but secretly the sum of all these three terms is actually a surface term at infinity, which somehow actually needs to know about all the dynamics in the system. Okay, so it's more conceptually confusing than the atom problem. And moreover, even if we could make this distinction, H coupling usually can't be ignored. So there's sort of a large region where the far region is interacting with the black hole system. You can't really turn that term off and study the problem separately. Now, what happened in the late 90s was that people found a very special limit where that coupling term really is small and can essentially be ignored for most purposes. Actually, probably not for all purposes, but for most. And that eventually became the ADS-CFT duality. So the technique, which I'll discuss a little bit later in the context of Kerr, made it possible to explicitly identify the quantum systems that describe certain special black holes or black brains for the first time. Okay, and because these systems that people encountered were explicit, well-defined, known to be unitary quantum mechanical systems, most people working in the field, I think, updated their priors strongly in terms of unitary. So we found some quantum system, it's a conformal field theory. We've been studying these for 50 years. We think that quantum mechanics makes sense. So it's probably going to be the case that black holes don't destroy information. But, just because we updated our priors, it doesn't mean that we actually have mathematical control over the evaporation process. Okay, so those examples came from string theory. And the quantum mechanical systems describing those black holes were sort of very complicated bound states of strings and branes, particular low energy limits where you could decouple the gravitational part of string theory. But, string theory is not really thought to be the crucial part of those constructions. I would say that this was kind of an illustration of an idea that we believe holds more generally. Yeah.
I was just curious. So this H coupling pops up in the string theory's integral on that in the string theory number theory, and that vanishes.
Well, I'll discuss what I mean regarding ignoring the coupling, but basically what happens in this construction. Well, I can do it on the next slide. Let me just. Okay, so, but we believe that this idea holds more generally, even when we can't explicitly construct the quantum mechanical system. So we still, to this day, don't have a microscopic construction of the four-dimensional Kerr black hole, but we believe, based on all of these other examples and analogies, that there probably is such a system. And since we can't construct it explicitly, what we try to do is understand its quantum mechanics by studying the Kerr black hole. Okay, so this is going to be the answer to the previous question. The limit that was kind of exploited to great effect in the early days of ADS-CFT was the extremal limit for the black hole and the decoupling limit between the region very close to the black hole and the region very far to the black hole. Okay, so when there are multiple parameters in a family of black hole solutions, the existence of horizon usually puts some constraints on the charges and angular momentum of the black hole. So the hole can't spin too fast or it'll shed its horizon, can't get overcharged, so the horizon goes away and you get to see a naked singularity. There are plausible mathematical demonstrations that you can't actually overspin a black hole or overcharge it. But it's thought that you can probably get arbitrarily close, or at least close enough to see some really spectacular effects. Okay. So the black holes that nearly saturate these bounds are called near extremal. And if you look at the black hole thermodynamics, you'll find that when you approach the upper limit for these bounds, the temperature of the black hole goes to 0. So it's a very large system, but it's becoming very cold. Okay. And as you take this sort of geometric limit, what happens is that the geometry outside of the horizon, very close to the horizon, undergoes a very dramatic process where a huge throat of infinite proper depth actually opens up right outside of the horizon. So the observer very far from the black hole doesn't really see anything dramatic happening. He'll be sensitive to this effect through certain signatures of things around the black hole. But it doesn't look like a dramatically different black hole very far away. But an observer very close to the black hole, for instance, who is co-rotating with the horizon, will basically experience a little mini universe all to himself. Okay. So this was sort of an early illustration of this idea in a paper by Bardeen, Press, and Tucholsky. You can sort of see they're keeping track of a couple of astrophysically relevant radii in the Kerr geometry, and as you dial the hole towards extremality, this throat is becoming infinitely deep, and all these radii are becoming very separated from each other.
Is that a figure from there?
Yeah. It's a pretty old illustration. I'm not sure if it was the first time. I doubt it was the first time that was understood. Probably Robinson Bertati was first. Yeah. Any questions about this? So this is just some, really dramatic prediction of general relativity. Maybe the most dramatic prediction of general relativity. So this throat region is approximately ADS2 times S2. So ADS2 is just hyperbolic space. So space with an infinite amount of volume, which is basically this statement that I said. This person very close to the black hole sees his own little mini universe with an infinite amount of volume. And it happens that this ADS2 factor actually has extra symmetries that the rest of the black hole space-time doesn't have. Okay. So what's happening in this very special limit is that the space-time is kind of bifurcating into two different systems. One, which is a flat space region where not anything very interesting is happening. That's sort of where we sit with our telescopes. The other region very close to the black hole, which looks very different, looks like an ADS2 times S2 throat. And they approximately decoupled from each other just because, at least for certain low energy observables, they are essentially infinitely separated. Okay. So that's the sense in which we're ignoring this H coupling term. These two systems are just becoming sort of geometrically separated. We can try to treat them separately. So we associate this ADS2 region to the black hole. That's going to be our sort of the arena for the effective dynamics of the black hole, because from the perspective of the far observer, all of that huge ADS2 region is just sitting right at the horizon. Okay, so he just thinks that's the black hole horizon and the dynamics associated to the black hole. And because for the person in that ADS2 throat, the far region seems infinitely far away, we just forget about it. And if we need to keep track of it, then we just replace the information about it with boundary conditions at the boundary of the ADS2 throat. Okay, so we have some observer down here. This is sort of where the black hole dynamics is happening. Anything that's going on out here very far away from the black hole, we can just replace with some boundary condition at kind of the mouth of the throat and treat the problem that way. Okay. And similarly, if you took a black brain rather than a black hole, then what you would get in this extremal limit is just a higher dimensional version of hyperbolic space. And that's really the place that ADS-CFT first emerged. This ADS is just the ADS CFT, and the conformal field theory was the quantum system which described the set of black brains. Okay. So this extremal black hole is kind of like a soliton. It's interpreting between two very symmetric but very different solutions to general relativity. Very far away from the black hole, it's just flat space. Very close to the black hole, this region that kind of snakes around in between the inner and outer horizons, that's the ADS2 throat. Okay. Any questions about that? Sure.
In the higher dimensional version of that Penrose diagram, is the brain actually in that space time? Like, can you draw? Is there a Penrose diagram this structure like that, like not ADS2, like higher dimensional?
Well, there's just non-compact directions, right? There's still a horizon.
Like brain in the Penrose diagram.
Well, I don't know what you mean by brain. I mean, if by brain you mean the curvature singularity, then for most.
Right, like I guess like people think of the brain like at the singularity.
This is the side of the duality where you don't have the brains, right? Because you've taken a strong coupling limit where the brains have back reacted into something different, right? So, you know, there's some sense in which the brains in ADS CFT are at the boundary of the ADS throat, but I don't know if you can really make it more precise than that. Okay, so the original idea of the ADS CFT correspondence, the way that people found it, was really just studying the response of the black hole to low energy probes. Okay, so we have this near extremal black hole, we throw some stuff at it, it's like spectroscopy. We don't understand this system very well. How do we learn about it? We shoot things at it and see what comes out, right? And if you do that with very low energy probes so that you don't actually disturb the system very much, then you can hope to get some information about the system itself, not just the system plus the thing that you shot at. Okay. So, you know, one thing that you can do, as I said, is to take this problem, and since most of the dynamics is going to be occurring near the black hole, you just replace this information about what's coming and going near the horizon with boundary conditions at the edge of the ADS2 throat. And then you study the dynamics inside of anti-de Sitter space. So stuff comes in, interacts in some nonlinear way, stuff goes out. And then you just attach this information back onto the far region and propagate it out to the far observer. And that gives you the answer. Okay. So this is just an exercise in matched asymptotic expansions. It's perfectly well defined. People know how to do it. But if the black hole is really a quantum system, then you can imagine that there's a different way to do that calculation, right? So since all of this region of space-time is really sitting right at the edge of the black hole horizon, you can imagine just replacing the dynamics in this ADS2 throat with the dynamics in the quantum mechanics subject to these sources that you've turned on from the far region, understand how the quantum mechanics responds to those sources, and then propagate that back out to the far region, okay? And in the best understood examples, we can actually do both of those calculations explicitly, and we find that they match. And that's basically the evidence for the ADS CFT course.
I read outside the black hole, you mean a couple short.
Well, it depends, yeah. It depends for what observer we're talking about. For the guy who co-rotates, it's a huge infinite volume space where the interactions are happening. But for the guy very far away, it looks like all the interactions are happening very close to the black hole.
You should rip all the way up to the horizon, right? I mean, basically.
This is the gray body, right? And the gray body factors go up.
Yeah. The gray body factors can be stuff which happens like out near the photon ring.
But the CFT includes the effects of the gray body.
I don't understand that as well. It is the case. Yeah, if you study sort of.
But this is very important to the photon, right? Because it would suggest that the photon ring lives in that right?
Yeah, well, to me, yeah, I think it's less clear, you know, when the black hole is not extremal, really what part of the space-time belongs to the black hole and what part belongs to the far region and in what region they're interacting with each other. So, you know, for a normal Kerr black hole, photon ring does reach out several Schwarzschild radii away from the horizon. And And there are excitations in that region, which normally we would associate to the black hole, like the quasi-normal modes. Certainly in anti-de Sitter space, we associate the quasi-normal modes to Ruel resonances of the thermal state of the black hole. But it's just a little bit fuzzier. The reason that all of the progress has been made on extremal black holes, in my view, is really just because that's the region where we kind of really do know how to where to put the stretched horizon for the black hole. It's kind of at the edge of ADS.
When we did the calculation matching the scattering to the CFT, we had to include the gray body. That was all the same on my calculation, but it doesn't look like a string decay until you include the black body factor, which cancels all sorts of others. The gray body factor. Yeah. So even there, that it's.
We have to be a little bit careful just because in the extremal limit, often the photon ring does actually go into the throat region. So it's not as if, the potential can have its peak actually very close to the throat, not necessarily very far from the black hole. But I agree that I don't have anything more intelligent to say about that, but it is true. That's an important piece, which sort of seems like it's more associated to the geometry far from the horizon than the rest of the calculation. Okay. So having this quantum mechanical system in hand basically allowed people to give a statistical interpretation to the black hole entropy. So you had quantum mechanical system, you just count the number of states for fixed charges and angular momentum, and a leading order in some approximation that simply gave you the exponential of the Bekenstein-Hawking entropy. Now, in these examples, since the black hole was extremal, what was really counted were the ground states in the quantum mechanics. So these black holes have a somewhat non-standard thermodynamic property that you can take them to zero temperature, but maintain a finite and in fact very large entropy. And that's a little bit non-standard. Most systems do not have huge macroscopic ground state degeneracies unless there's some very special symmetry protecting that degeneracy. Now, in the case of these original extremal black holes and black brains, there was extra supersymmetry inherited from the superstring, and that basically protected the degeneracy. So it wasn't a huge surprise that you had all of these states at the vacuum. But for instance, it's impossible to make the four-dimensional Kerr black hole supersymmetric. So it's not obvious that you would naively expect the quantum mechanical system dual to that black hole to have all of these states. Yet the leading order calculation in black hole thermodynamics actually predicts a huge ground state degeneracy. So a long-standing question has been, do quantum corrections lift the ground states for that black hole? Sort of naive expectation would be yes. On the other hand, Kerr has lots of interesting hidden symmetries. We don't actually understand the symmetry structure of quantum gravity completely. So it could have been that there's some hidden symmetry we don't know about protecting the states. We sort of need to actually just do the calculation and figure it out. Okay. There's another puzzle related to the low temperature thermodynamics for Kerr, and actually even for Reisner Nordstrom. So if you just calculate what is the thermodynamic energy above extremality for these black holes at low temperature, so very close to the vacuum, you find that it scales quadratically with the temperature of the black hole. So that's this curve here. On the other hand, the generic Hawking quantum that's being emitted by the black hole has an energy that scales linearly in temperature. So at some point, those two curves will intersect, and below that point, which is basically set by the angular momentum, the emission of a single Hawking quantum would carry away more than all of the energy available to this black hole system. So that's not really an equilibrium process. So something funny seems to be going on at these very low temperatures. And I think this was first pointed out in a paper in the early 90s. And basically the way to think about this paper is just that at temperatures below this point, which people used to call the gap scale, there's going to be large corrections to the thermodynamics of this black hole. And they sort of identified several different possibilities for what the change in the spectrum might look like, how this might be resolved, but they didn't manage to actually say which one of the possibilities would be realized. And we realize now that's because actually multiple different possibilities can be realized. So just to kind of understand what we expect might be happening, we know that the black hole thermodynamics is some coarse graining of a quantum system, right? So it's sort of the first leading approximation to the quantum mechanics. We don't know the exact density of states for these systems. We're calculating it sort of in a perturbative expansion. So, we imagine with the first couple of orders in the calculation, we have some coarse-grained approximation to where the different states for this Hamiltonian lie, but you see we can't really resolve exactly where they are. The widths are wider than the eigenvalue spacing. But as you include more and more subleading corrections, you get to actually resolve precisely where these little spikes in the density of states are. So it could be that the leading coarse-grained approximation tells you there's a lot of states right here, but then once you actually calculate the corrections, you'll see that they're actually spread out in a little band about the vacuum, okay? And that's what we're going to see for the Kerr black hole. Is that clear?
You said that there's many ways, multiple ways to, I guess, undo the coarse grading. So how do you determine what to do?
Well, I wouldn't say there's multiple ways to undo the coarse grading. I mean, people believe that there is one quantum system with a particular spectrum related to the black hole. There's multiple ways that this puzzle could have been resolved, basically with different properties of the spectrum. So one property would have been that actually below this gap scale, there was just actually a gap in the spectrum of the black hole. Okay, that would have solved these problems. When you have a huge gap in the spectrum, you're just not allowed to apply thermodynamics in that gap. Thermodynamics requires that there's a huge number of densely spaced states, which you can kind of coarse grain over. If you have a gap, you can't do that. That was one possibility, and that turns out actually to happen for supersymmetric black holes. So you can actually calculate that gap and match onto the expectation. But another possibility is just that actually there isn't any effective gap in the spectrum, but all of those ground states are not actually ground states. They get spread into a dense energy band right above the vacuum. And it appears that that's what happens for non-supersymmetric black holes like the Kerr black hole. Okay, so what we did was to compute sort of the relevant leading quantum correction to this low temperature thermodynamics for the Kerr black hole, and we found that this correction apparently lifts the ground state degeneracy. So at least in this approximation, the density of states vanishes at 0 energy above extremality. So we know at least that there are not e to the s number of states at 0 energy. We can't really resolve much smaller eigenvalue spacing, so we don't know, are there like 5 states here and then a ton here? We can't resolve things of order e to the minus s in this density of states, but we at least know that there's not e to the s states sitting at the vacuum, which is what the leading order calculation said.
If I remember correctly, when that paper, Pascal and friends wrote that paper, the general impression was that once you hit that low energy, the system becomes strongly coupled, and you couldn't really calculate anything.
Yeah.
I don't think anybody really tried to do it until recently. In hindsight, was it guaranteed? Was it guaranteed that it was possible, or did we just get lucky?
I don't think so. I'll say something about this at the end. I mean, really the reason why this calculation is possible is because now we know that we can kind of simplify the problem by looking at the throat. And there, as you know, we have a calculation which we think we can do, which reliably calculates this correction, but still nobody has done the calculation using the full geometry to get this t to the 3/2, which I'll discuss. And I think that's how they would have thought about the problem. Before ADS-CFT, they would have thought, I need to do a calculation that uses the full near-extremal Kerr and see that the ground state degeneracy is removed. And still nobody's managed to do that. and seems like it still might be intractable. So,
I see.
I think the developments of the late 90s are kind of crucial in order to be able to turn around and try to solve this problem.
Did you also just suggest that this could be only a piece of the answer, and there might be
There definitely will be other corrections to it incur. For instance, the super radiant effect, I think, is going to be another very important piece of calculation, which I'll discuss later. We've ignored, but can probably be incorporated. And you can also, as I'll discuss, this correction to the low temperature thermodynamics changes the amount of energy available to the black hole above extremality at low temperatures, moves it above the line for the Hawking quanta, so that actually you can still apply thermodynamics at these low temperatures.
You said like these quantum corrections are lifting the ground state degeneracy, right? But
yeah,
it's really like very dramatic. That sort of makes it sound like it's like just a splitting, right? But it's really going from a e to the s naught states to 0 states, right? So it's,
well, but the e to the s naught states are getting spread out above the map.
Yeah.
So it's like a huge number, which thing is, I'll have a little cartoon for this later.
So kind of like black hole hyperfine splitting in a way.
That's the way to think about it.
Okay.
Yeah. It's like the leading calculation has huge degeneracy, and then we generate little e to the minus s naught spacings in the full model. Okay, so in the time that's left, I'm just going to sort of outline the technical details of the calculation, not too technical. So one kind of crucial piece of the ADS-CFT dictionary tells you how to compute the partition function trace e to the minus beta h in quantum mechanics in terms of gravitational variables. So for instance, when we don't actually know the explicit quantum mechanical system, we try to study its partition function by doing gravitational calculations in the ADS throat. Okay. Now, this is a very tricky formula because the right-hand side is actually very poorly understood. In fact, it might actually be mathematically ill-defined, but it's primarily studied in the saddle point approximation. Okay, so this is some huge infinite dimensional integral. We can't do it exactly. We don't actually even understand all of its properties, but we try to approximate it using saddle points, and we usually get pretty interesting answers which confirm expectations that we already had. That's why we believe that something like that makes sense. So the right-hand side means that we integrate over metrics and matter fields in anti-de Sitter space subject to some boundary conditions which are picked out by the ensemble or the problem that we're trying to solve.
You mean two-dimensional anti-de Sitter space here, right? Or
for the black hole,
but
but for brains it would be higher dimensional space. Okay, so the picture is that we're fixing some boundary conditions at the mouth of the throat, and then we're integrating over fluctuations and metrics in the interior of the ADS2. Okay, so we're trying to do this huge functional integral over metrics weighted by the Einstein-Hilbert action, and we say what are the asymptotics of the metric near the edge of ADS. The only way we know how to approximate it is by saddle point. Now, saddle point means solution to the classical equation of motion subject to the boundary conditions. And in this case, the solution is just neck, near horizon extreme curve, the sort of version of ADS2, which is slightly warped because the black hole is rotating. So this is its metric. It's relatively simple if you've ever encountered the full four-dimensional Kerr metric. And as I mentioned, it's simple basically because it has extra symmetries. It has conformal symmetry, which the full Kerr geometry does not have. So at zero temperature, at precisely zero temperature, you can approximate this path integral using the leading saddle, and that reproduces for you the extremal Kerr entropy. So you do this gravitational path integral, you get e to the 2 pi j. 2 pi j is the entropy of the extremal Kerr black hole. So that's what you would expect for the zero temperature partition function. Yeah.
If you do this path integral, because we're like in a new region, like there's also the Gibbons boundary term, but that boundary isn't like at infinity, it's like still like a near. Like how does that make sense?
Well, you're imagining basically that you have replaced all of the information about the far region with information at the boundary. So the boundary kind of incorporating information about the UV, the stuff which is very far away. So it's supposed to keep track of some amount.
Like if you don't do the near curve, then you still get the right answer, right? And if you take the boundary to be actually the boundary of asymptotically flat space, you still get centric. Isn't it kind of strange?
Yeah, if you do the full 4-dimensional calculation, you're also going to get e to the 2 pi j. Sort of what's interesting about the ADS-CFT correspondence is that you can actually also do it just using the near region and still get the right answer.
So does that actually come from the boundary thing? Or
does this crucially does depend on the boundary.
The other thing is here.
Yeah. Okay. So the first correction to this, so this we know about. This just comes like from the ordinary Gibbons-Hawking calculation in the full Kerr geometry. But the first correction comes from integrating over the fluctuations about this background metric. And that's really where all the subtleties in the calculation lie. So if you were calculating this partition function in quantum field theory, then that correction is always ultraviolet divergent, basically because you integrate over fluctuations with arbitrarily short wavelengths. There's infinitely many of them, you get infinity. In a UV complete theory of quantum gravity, we would expect that correction to be finite, but we can't actually do that calculation, especially not in the Kerr throw. So we can only really try to do part of it. Okay? Fortunately, it turns out that there's still some universal information in that one loop correction. So part of it comes from short distance, non-universal UV physics, but part of it just comes from low energy fluctuations of massless fields like the graviton in the throat of the black hole. Okay, and that part actually is universal because it's related to very low energy stuff. So one of the things that these fluctuations do is to produce sort of a renormalization of this ground state entropy. So if the black hole really did have a ground state degeneracy and we start computing quantum corrections, we'd find that S0 was just the leading approximation to the ground state degeneracy. There are corrections sort of in a series in 1 by S0 or 1 over the area of the black hole. And these types of fluctuations fix the coefficient in the log S0 term. So that's something which was studied by Ashok Sen in extraordinary detail about 10 years ago. But he calculated these using gravity and actually was able to compare to some microscopic calculations in string theory and found precise matches in all of the cases where we actually had a microscopic description. But importantly, these matches were only possible for supersymmetric black holes. Those are the only ones which we actually have microscopic descriptions. However, there's a subtlety in Sen's calculation, which turns out to be more or less irrelevant for the supersymmetric black holes, but which is actually crucial for the non-supersymmetric black holes. Okay? So, when we try to do the integral over these fluctuations about neck, we take the metric, we expand it around the background field, the neck geometry, and then we try to do the integral over these fluctuations. So we basically take the Einstein-Hilbert action, expand it to quadratic order in the perturbation, and we have to do a bunch of Gaussian integrals, basically. You remember that you do a Gaussian integral with an eigenvalue in the exponent, you get 1 by square root of the eigenvalue. And if you do a product of Gaussian integrals, you get 1 over the product of square roots of eigenvalues. Okay, so that's a finite dimensional integral. Here we're trying to do an infinite dimensional integral, but because it's a linear problem, this operator D, the kinetic term for the perturbation, is really just an infinite dimensional matrix. Okay, so if you decompose this perturbation into the eigenvalues for H, then you just get an infinite product of Gaussian integrals, which you can do using this formula. So this integral appropriately regularized is just 1 by the determinant of that differential operator. So the one loop correction is just a regularized determinant, and Sen was able to extract some universal information from it compared to quantum mechanics, and he found a match that kind of gives us more confidence in this sort of gravitational path integral approach to the problem.
You also take the Diffie-Hughes determinants and stuff.
You do, yeah. It won't be relevant for this calculation, but to get the match, you have to keep track of gauge fixing and ghosts and all that stuff. Okay, now there can be a subtlety though in this procedure when this differential operator has 0 nodes. So if you do a Gaussian integral but the eigenvalue is 0, then you're just integrating over a non-compact domain with no suppression, so that's just going to diverge. Right? Equivalently, the answer for the Gaussian integral is 1 by lambda, so if the eigenvalue vanishes, that obviously blows up. Okay. Now, it turns out that D actually has infinitely many zero modes in NEC and in the ADS2 throw. You can write them down explicitly. They're normalizable modes, so according to all the rules that we understand, we're supposed to integrate over them. But if we do, then we would find that the path integral is infrared divergent. And that signals a subtlety in the extremal limit for black holes, which we might have expected given this work by Trivedi, Preskel, et al. Something a little bit funny is going on at low temperatures, which we have to understand. So this is a problem which doesn't actually arise for higher dimensional black brains and higher dimensional ADS spacetimes, is particular to ADS2. Okay, so different avatars of this infrared divergence have shown up in the literature in the past. It's basically happening because ADS2 is a low dimensional system with long range forces. When you have a low dimensional system with long range forces, the lines of force don't have enough directions to spread out in, so they don't become small at large distances, which means that back reaction will be very important. And in particular, if you try to put some finite energy excitation inside of the ADS2 throat, it's going to source a gravitational field which actually becomes very large at the boundary of anti-de Sitter space. It sort of destroys the asymptotics. And what that means is that these small excitations in the ADS2 throat, which we thought were supposed to be decoupling from the far region, are actually still talking to the far region. Because you excite them in the throat, they become big in the region that we thought was dividing the black hole from the far region. Okay. So there's some type of interesting failure of decoupling, and the subject was kind of dormant for many years until this important work by Maldacena, Stanford, and Yang, who kind of identified a pseudo-Goldstone boson description of this infrared divergence. I don't want to go into the details, but there's a certain symmetry breaking pattern related to that conformal symmetry that I mentioned in ADS2, and you can kind of use that to arrive at a model which is responsible for this infrared divergence, which then you need to treat exactly. And if you do that, then things go back to normal and you can apply the normal rules of ADS-CFT. So in particular, if you treat this piece, this infrared divergence classically, you're able to reproduce the near extremal entropy of the ADS2 black hole.
So these zero modes then don't occur in standard CFT extremal black hole cases.
They occur for extremal black holes in ADS, yes.
Okay,
but they don't occur for like a black brain, for instance, which would be described by English. Yeah. Okay, let me just skip this. Okay, so the point though is that treated quantum mechanically, the mode actually dramatically alters the low temperature thermodynamics. So that was sort of first put together for the Reissner-Nordstrom black hole, which is spherically symmetric and therefore sort of technically much easier problem in a paper by Luca Murthy and Turiachi in 2022. We basically adapted this calculation to Kerr, where it's much more difficult, but the sort of conceptual steps are mainly the same. And there's another related work which came out shortly after ours, which does the same calculation and gets the same answer. Okay. So since I'm basically out of time, I'm going to go through this very quickly. But the basic idea in all of these works is that when we take this scaling solution, when we take the limit that zooms in on the region right outside of the black hole, we keep not only the leading term, which is the NEC geometry, but also the subleading term in the low temperature expansion. Okay, so this is kind of the geometry which we always used in the past, but which led to all of these conceptual puzzles. Now we keep the leading correction because we sort of know that the throat region has not completely decoupled from the far region, and this correction to the metric is basically coupling this throat region to the far region. Okay? So it's very complicated. It's actually more complicated than the Kerr metric itself, but you can calculate it explicitly. And that metric perturbation induces a perturbation in that kinetic operator, which we were using to compute the partition function. And you can just use first order perturbation theory to compute the change in the eigenvalues of those zero modes using the perturbed kinetic operator. And you actually get something extraordinarily simple. So to give you an idea, sort of just storing the Riemann tensor in this geometry and text expression takes about 5 megabytes. It's an extraordinarily complicated geometric quantity, but you do all of the integrals and you get something extraordinarily simple, which usually tells you that there's something else going on. So what's basically happening is that this finite temperature is actually lifting the eigenvalues of these zero modes and regulating the partition function. So if you compute that determinant explicitly, you'll find a change in the logarithm of the partition function, which is proportional to a logarithm of the temperature above extra mil. Okay? And that's important because the partition function with this correction is now actually becoming small at low temperatures. So previously, before we had the quantum correction, at low temperatures, the partition function was approaching e to the s naught. That's very big. But we computed this correction. Now we take t to 0, actually partition function is becoming very small. When the partition function becomes very small at 0 temperature, that means there's not a huge ground state degeneracy. Okay?
Did you explain exactly where we got the power of 3 halves, right? Because if you had worked in the grand canonical for J, like here you.
Yes, so that's a very tricky point, actually, especially for Kerr, because there are another set of zero modes which people thought existed for this black hole, but which actually, when people like us tried to construct, didn't manage to. So that's still a little bit of a puzzle. But in a particular ensemble, this coefficient is fixed to be 3 halves.
Right.
And it is related to symmetry breaking.
I was wondering if there were other zero modes that you might have had to have regulated that you didn't hear. I guess
there is. Let me, maybe if people want to stick around for the question session, but it's that'll be a little bit of a distraction. So we interpret this result as saying that instead of a e to the s naught number of states sitting right at the vacuum, actually all of those states have gotten smeared out in a very dense energy band above the vacuum. Okay, and then you can check that the change to the thermodynamics means that actually you still can apply standard thermodynamic analyses in this dense energy band. And so we don't have this gap, which could have resolved the problem. Instead, we have a very dense energy band and can still apply thermodynamics. Now, we'll never actually be able to compute these exact values because the eigenvalue spacing here is going to be like e to the minus s naught, which is like e to the minus 1 upon g Newton, which is a non-perturbative effect in gravity, which we just don't have any control. But at least we know that they're not all sitting right here.
What's the upper limit to this energy band? Like how much do they stretch out?
Well, they probably stretch out about order e to the j to the minus 3 halves. There's sort of a scale in the problem, and you expect them to kind of fill out in that band, what people would have called E gap. Okay, so last piece is just when can we trust this result? It's obviously not true everywhere. We took a low temperature scaling limit. It's also not going to be true at arbitrarily low temperatures. So when this small prefactor starts really competing with this huge other factor, then the approximation is going to break down. So we can't go to temperatures which are exponentially small in this extremal entropy. That's equivalent to the statement that we can't resolve eigenvalue spacings of order e to the minus s naught in the density of states without doing a non-perturbative calculation. And similarly, when the temperature gets too big, then just the near extremal approximation itself breaks down. So there's sort of an interval of temperatures where this is the dominant effect, but that's enough to show us that we don't have this enormous ground state degeneracy predicted by the leading order calculation. So maybe I'll just leave a couple of remaining questions on the board. One of them is related to Andy's question. There are other very important physical effects that are there for Kerr, which are not there for supersymmetric black holes, like superradiance, which we expect to give finite widths to these states that the entropy is supposedly counting, and those need to be incorporated carefully. And I think it would also be interesting to reproduce this this behavior, this lifting of the ground state degeneracy using a full black hole calculation rather than just the throat calculation, because it can be very tricky to actually understand how to connect the throat calculation to the full far region when you're not precisely at extremality because of this failure of decoupling. So it would, I think, be reassuring if we could get the same behavior from a full black hole calculation that would tell us that it's really a physical effect. So I'll stop there.
Quick question. There's been some work on observational implications of behavior of curve. Morphology of magnetic fields, for example, and what it would look like in super high spin case. Yeah. But then I noticed you said something about things would change if you had matter close to the horizon, and then in our physical instances where you get a lot of matter, so like tidal disruption events, for example, where a whole star is shredded. But does this break down when that happens, and then does it go back into some symmetrical?
Yeah, I mean, these calculations are, kind of the pristine, isolated black hole, which we get to study not in an astrophysical setting, but just in our minds, because we're interested in sort of these conceptual questions about the spectrum and how it is that the black hole is a quantum mechanical system. If you put this cold black hole in interaction with a huge chaotic ergodic plasma or something, then the plasma effects will be much larger than these very fine-grained quantum mechanical effects, right? So there's one question whether or not you can even get a very high spin black hole in an astrophysical setting. Second question, whether or not even if you did, what would be sort of the consequences for the matter system around the black hole enforced by the extra symmetries of this high spin black hole. That's something that I've worked on. Other people associated to the BHI have worked on. But this calculation is completely irrelevant to M87 or any other high spin black hole surrounded by a huge classical chaotic plasma, something like that. This is sort of related to a conceptual question. If we had an isolated high spin black hole, what would be its properties? The classical dynamics will dominate almost everything for the astrophysical black hole.
Just get a sense of the scale. Did you compute the heat capacity for the M87 case, or just what the scale of the gap basically for M87?
No.
But I think it's really small. Would be the
yeah.
Like 10 to the minus something.
100?
Have its time.
Yeah.
It would be M87. The inverse force power of M87 is 2 periods.
Since the states, I guess, it's mirrored out due to quantum effects, is the way how you do the microscope counting for the extreme curl gate, I guess, somewhat qualitatively different from the traditional like microscope counting for those SUSY black holes, right?
Well, in some sense, I mean, for the SUSY black holes, there's exact degeneracy. So you fix the charges. You say this is precisely how many states we have for the fixed number of charges, blah, blah, blah. But, entropy means something for a, gas in a box, right? And it just means that you need to coarse grain a little bit over energy. So instead of making that precise statement, we just say we fix some energy band and we ask roughly how many states are there in that energy band, and the answer will be coming from this calculation.
And I guess another question. So I've always been curious, is there another, so typically people work with extreme black holes have to see the ADS, but in the case of like a short shield near horizon regions like Rindler, could you do like a similar sort of argument for Rindler space for like a short-tail black hole?
Well, the problem is for the Schwarzschild black hole, there is really no separation between the black hole system and the far system. So that's like an extreme example of Andy's question, where there's many Schwarzschild radii where the two systems are interacting with each other, and it's just not clear how to make it. We hope that there is some sense in which you could make a separation like that, but it's much harder, and we just don't know how to do it. There might be some interesting way to formulate the problem, but I think the issue is just the sort of that coupling term is actually very large in that example and can't be neglected. That might be like the more important term, and then you have to solve the problem in a different way.
There is one wacky loophole where you can really do the computation with the full geometry, right? But that's with these index type black holes. But I think this is something Sen has been looking at recently.
Yeah, that's true.
So at least in principle, one can do it, but they're for rather exotic.
But it's also an example where this T to the 3.5 doesn't show up.
Exactly,
right? So the effect is
yeah.
missing when
Precisely.
you can do it, and when it's supposed to be that you can't do it. So I think there's still interesting directions.
Thank you.